Hello, my name is Christian Lee, and this is my video for Lab 4 Oscillation. So the main idea of this lab is to observe and predict the motion of an object oscillating on a spring traveling in an arc-like trajectory. Throughout the lab, we'll compare the predicted and observed position of our object over time, as well as the change in energy of our system over time. There's three main applications that this lab will draw upon. The first is the equation that relates the period of our oscillation t to our spring constant k. You can see that equation in the red box below. The second is our conservation of energy principle, which tells us that the total change in energy is equal to the sum of the change in rest energy, kinetic energy, and potential energies, which is also equal to the sum of external work and change in heat. The third is Newton's second law of motion, which is what we will use to take our net force and use that to update our velocity and our position. The main assumptions that this lab takes into account are first that the total change in energy of our system is equal to zero. That means there's no external work acting on our system, and there's no energy lost through heat. Said system includes our object, the spring, and the earth. You'll also be neglecting all forces acting on the object other than the gravitational force from the earth and the spring force from the spring. So let's take a look at our position graphs. Now, the period of our oscillation can be calculated by looking at the adjacent peaks and adjacent troughs of our x position versus time graph. Through this process, we can see that the period of oscillation comes out to be about 1.709 seconds. Let's look at our glow script code. So our spring constant here can be calculated using the mass of our ball, as well as the period of oscillation that we just found. S can be found by subtracting the relaxed length of our spring from the stretched length of our spring. Those two numbers can be used to calculate our spring force, and then our gravitational force is simply negative mg, in which g is acceleration due to gravity. By adding those two forces together, we get our net force, which is then used in our momentum principle to update our velocity and position, and construct our model. So the model is compared to our experimental data in these two graphs here. And as you can see, in our x position, it's pretty accurate throughout the process. But in our y position, it quickly begins to deviate from our experimental data. Why is that so? Well, first, this could simply be due to human error. But second, is that in actuality, the total change in energy of our system is not zero. This is due to external work acting on our system from, for example, air resistance, and also change in heat of our system as from friction of our spring oscillating back and forth. Now let's look at our change in energy graphs. There's two main things to note here. The first is that our graph for potential gravitational energy and potential spring energy are basically inverse of each other, in that they have the same periods, but as one increases, the other decreases. Now, if we think about our model, this makes sense. When the ball drops lower to the ground, potential gravitational energy will decrease. But at the same time, the spring is being stretched more, so potential spring energy will decrease. The opposite is true when the ball is rising up. Now, the second main thing to note is that delta E, or the total change in energy, is zero the entire time. This supports our energy principle, since we are assuming that work and external work and change in heat are going to be zero. Now, if you recall from earlier, we used the peaks and troughs of our x position versus time graph to find the period of oscillation. What if instead we used our y position versus time graph? Well, t comes out to be about 1.425 seconds instead of 1.709. And by using our new t, we can see that the first few seconds of our y position versus time model are now much closer to our experimental data. However, later on, it still begins to deviate, so that doesn't change. And as for our x position versus time graph, it stays the same. It stays pretty much the same the entire time, although it is a little further off than if we had used just our x position versus time graph to find our period of oscillation. That is all for this video. Thank you so much.